So, as we were discussing about the classification of optimization in the last video lecture, I will be moving ahead with the same classification. So, in the last video lecture, I discussed about the classification based on nature of design variables. There, I told you that it is being classified into static optimization and dynamic optimization. Static optimization problem is to find values to a set of design parameters that make some prescribed function of these parameters minimum subject to certain constraints. And dynamic, or you can say trajectory optimization problem, is that problem where the objective is to find a set of design parameters which are all continuous functions of some other parameter that minimizes an objective function subject to a set of constraints. The next classification is based on physical control. It has been divided into two: optimal control and suboptimal control. So, an optimal control problem is a mathematical programming problem involving a number of stages where each stage evolves from the preceding stage in a prescribed manner. It is usually described by two types of variables: the control, that is design, and the state variables. The control variables define the system and govern the evolution of the system from one stage to the next, and the state variables describe the behavior or status of the system in any stage. The problem is to find a set of control or design variables such that the total objective function, also known as performance index, over all the stages is minimized subject to a set of constraints on the control and state variables. The next classification is based on the nature of variables. So, based on the deterministic nature of the variables involved, optimization problems can be classified as deterministic and stochastic programming problems. So, stochastic programming problem is an optimization problem in which some or all of the parameters, that is design variables and pre-assigned parameters, etc., are probabilistic, or you can say non-deterministic or stochastic, and vice versa is for deterministic programming problem. The next classification is separable, or you can next classification is based on separability of the functions. So, depending upon this, it can be classified into two, that is separable and non-separable. Now, next classification, separable and non-separable. So, a separable programming problem is one in which the objective function and the constraints are separable, and the vice versa is for non-separable. Now, based on the nature of equations involved, it can further be classified into linear, quadratic, and non-linear programming. So, or you can say that is the another important classification of optimization problem. So, according to this classification, as I've already told you, optimization problems can be classified as linear, non-linear, geometric and quadratic programming problems. So I have missed this geometric programming point. You can note it down. So this classification is extremely useful from the computational point of view, since there are many spatial methods available for the efficient solution of a particular class of problems. Thus, the first task of a designer would be to investigate the class of problem encountered. So, starting with the first point, nonlinear programming problem, that is, if any of the functions among the objective and constraint functions is nonlinear, the problem is called nonlinear programming problem. This is the most general programming problem, and all other problems can be considered as special cases of nonlinear programming problem. Next is quadratic programming problem. A quadratic programming problem is a nonlinear programming problem with a quadratic objective function and linear constraints. And the last point of this classification is linear programming problem. Here, if the objective function and all the constraints are linear functions of the design variables, the mathematical programming problem is linear programming problem. So, the next classification is based on the permissible nature of design variables. So, depending on the values permitted for design variables, optimization problems can be classified as integer and real valued programming problems. Kindly correct it. It is written as inter programming. It is not inter, it is integer programming problem. So, in integer programming problem, if some or all of the design variables x1, x2 up to xn of an optimization problem are restricted to take on only integer values, the problem is called integer programming problem. On the other hand, if all the design variables are permitted to take any real value, the optimization problem is real valued programming problem. And the last classification is based on the number of objective functions. So, depending on the number of objective functions to be minimized, optimization problem can be classified as single and multi-objective programming problem. So, like I've already stated in this slide, I have given the statement of an optimization problem. Any optimization problem stated in this way, which is having one fx, is single programming problem, single objective programming problem. Single objective programming problem. And multi-objective programming problem can be stated as like where there will be number of fx. Here in the single objective problem we have only one fx. When there will be many objective functions like f1x, f2x, f3x, then that type of problem will be called multi-objective programming problem, where f1, f2, fkx, all the objective functions are to be minimized simultaneously. So I'm ending the class here. We will continue further in the next video lecture. Thank you.